Hello everyone, I'm Qipeng from Hong Kong University of Science and Technology. I'm going to present our paper, MDPFuzz, Testing Models Solving Markov Decision Processes. This work is co-authored with Yuan Yuan and my advisor Shuai Wang at HKUST. In this work, we design an efficient fuzz testing framework to find the cross-triggering state sequences in state-of-the-art model solving MDPs. Let me first introduce the background of our research. Our tool, MDPFuzz, tests the models that solve Markov decision processes, and MDP provides a mathematical framework for modeling the sequential decision-making problems. And it has been applied in many real-world scenarios like self-driving, robot control, aircraft clearing avoidance, and games like Go and video games. To solve MDP problems, there have emerged many efficient techniques in the AI research community. Like the well-known AlphaGo adopted reinforcement learning to train a model that can beat the top Go players. And in recent years, there are many self-driving cars that apply AI techniques like deep neural networks, reinforcement learning, and imitation learning to train a model with high performance to help the driver make decisions. Despite the good performance of these methods, none of them can provide a rigorous guarantee that no failure will occur when the agents make decisions using these models. Especially in security and safety critical scenarios, the failures are intolerable, like the crashes in self-driving cars and drones, or even the fallings of expensive robots will cause great damage to our lives and properties. Given that said, it's very important to test these models that solve MDPs. But existing research is not sufficient to test these models comprehensively. There are a couple of limitations that prevent applying existing testing techniques on models solving MDPs. Firstly, previous works that test deep learning usually focus on finding single frame mispredictions. However, as shown in Figure 1 and Figure 2, a single frame inconsistent behavior can't result in a crash, as a well-trained model can quickly recover from the short-term inconsistencies. We find that when 1% of the decisions of the RL-controlled vehicle are mutated, it can't result in a collision across all the 1,000 runs as shown in Table 1. But the crash feasibility increases only slightly when many decisions are changed into inconsistent stages. And the second limitation of existing techniques is that modifying one or several intermediate states will result in an unrealistic sequence. If we mutate an intermediate single frame, the resulting sequence is broken as the adjacent states need to be continuous. And also the state transition function in MDP is not differentiable. This makes it very difficult to apply the objective-oriented generation methods like is done in previous white box deep learning testings. So to address the limitations and the challenges mentioned above, we propose our testing framework MDPFuzz. We first present an overview of our technique. Instead of mutating intermediate states, MDPFuzz selects the initial states according to the state's local sensitivity. And also, we guarantee that the mutated initial states are valid and solvable. MDPFuzz is guided by cumulative reward and the state sequence freshness, and we also incorporate a Markov property when computing the sequence freshness. Figure 3 depicts a cross-triggering sequence found by MDPFuzz, which shows that the whole sequence is realistic since we only modify the positions of the vehicles on the road. And the model control the vehicle, which is the black car in the middle of the image, crashes into the fence by taking the actions from a SOTA IR model. Figure 4 illustrates the workflow of MDPFuzz, where MDPFuzz selects and mutates initial states and feeds the initial states to the target agent model. The target agent model will take the actions and the environment will step into next states according to the transition function T. The environment will also return the state sequence and the cumulative reward to MDPFuzz. Let's look into the first component of MDPFuzz. Sensitivity computes the local sensitivity of the cumulative reward with respect to the changing of the initial state. It estimates a seed's potential to provoke diverse behaviors of the model. As shown in Figure 5, we are more interested in the initial states of the red points, whose sensitivity is relatively higher. And a small modification of the initial states will induce very large reward changes. Thus, we assign more energy to the seeds with higher sensitivities, and these seeds are more likely to be selected during fuzzing. Also, we managed to estimate the state sequence freshness to guide MDPFuzz. We utilize Gaussian mixture models to estimate the probability density distribution of the state sequences that are already covered by MDPFuzz. Then a new sequence with diverse patterns will induce lower density, and the lower density indicates a higher freshness. We are interested in these sequences that are not covered by previously found sequences, and we will maintain them for future mutations. Specifically, sequence fresh incorporate Markov property to efficiently estimate the density of the sequence distribution. That is, we only need to estimate two probability density functions, which are the joint distribution of ST+1 and ST, and the distribution of ST. In this way, we can efficiently estimate the freshness of the sequence at a constantly low cost. In contrast, the naive distance-based method is quite expensive when the corpus size becomes very large. Last but not least, MDPFuzz is also guided by the cumulative reward. A lower reward means that the risk of the model failures is higher. In summary, MDPFuzz selects seeds with higher sensitivity and prioritizes seeds with higher freshness and lower cumulative reward. And this is the design for MDPFuzz. In the following, we will introduce the experiments setup. We use several SOTA models in different MDP scenarios, like self-driving, aircraft collision avoidance, and two different games that are commonly used to benchmark reinforcement learning. And MDPFuzz aims to find crashes in these models. The definitions of the crashes are scenario-specific. In self-driving, the crashes are collisions between the vehicles, and in the bipedal walker, the crashes are the failings of the model-controlled agent. We also guarantee that the mutated initial states are valid and an optimal solution exists. Also, the simulation platform will reject the invalid initial states, and the strategies are similar for different scenarios. We implement MDPFuzz in about 1,000 lines of Python code, and it's available at this GitHub repo. In the following, we present the evaluation results of MDPFuzz. We first show the performance of MDPFuzz on finding crashes on different models and MDP scenarios. The sequence lengths, which are the numbers of the frames in the table, are different for different scenarios, and the users can utilize a larger number of frames to stress the model. During the 12-hour fuzzing, we are able to uncover 80 to 160 diverse cross-triggering state sequences. And also, MDPFuzz only consumes a small proportion of the total computation time for the real-world MDP scenarios. And we conclude that MDPFuzz efficiently finds the cross-triggering state sequences across different models and scenarios with only modest overhead. We show some cross-triggering state sequences found by MDPFuzz. And the audience can also refer to our website or scan this QR code for more results. Next, we show the effectiveness of our component sequence fresh. From figure 9, we show that with sequence fresh, MDPFuzz can find crashes more quickly compared to the results without the guidance of sequence fresh. And also, as shown in figure 10, the found sequence results in a larger covered area in the estimated distribution compared to the distribution without sequence fresh. This further indicates that with the sequence fresh, MDPFuzz is able to increase the diversity of the covered sequences. The results prove that sequence fresh is efficient and can help the MDPFuzz to cover more diverse state sequences. With the found cross-triggering state sequences, we analyze the root cause of the crashes. We plot the patterns of the neural activations by a widely adopted projection technique, TSNE. The neural activation of cross-triggering state sequences found by MDPFuzz have a clear boundary with normal and randomly mutated sequences. The results indicate that the cross-triggering states can trigger the model's abnormal internal logics. And we conclude that although the cross-triggering initial states are considered normal from the MDP environment's perspective, they induce distinct neural activation patterns. The findings of the root cause inspire us to enhance the model's robustness by developing an abnormal neural activation detector. We train a mean shift cluster using the normal and the abnormal neural activation patterns. The results show that we can achieve a very good performance in predicting abnormal neural activations with AUC close to or higher than 0.8. And also, we managed to boost the performance of the DNN-based ACAXXU model, which is the aircraft collision avoidance system, by fine-tuning the model with cross-triggering state sequences found by MDPFuzz. In sub-figure B, we show that after repair, MDPFuzz finds much smaller number of crashes during the same 12-hour fuzz. And we conclude that using the findings of MDPFuzz, we can develop an abnormal internal logic detector and fine-tune the models to improve their robustness. Thanks for your listening, and we appreciate any questions and comments regarding our paper.